Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution. And in particular, we're going to describe some of the details of what the core of a star that has undergone the process of supernova, what that core can become. And if you remember in the previous video, we talked a little bit about what it means when a high-mass star undergoes core collapse. And then, of course, the energy of that collapse causes the star to explode. And in that video, we talked about how if the core of the star that survives the supernova is of a particular mass, it can become an object called a neutron star. And if you remember from that video, what that means is that all of the material of this once iron core is crushed under this incredible force of gravity, so that all the protons and the electrons will merge together to become nothing but neutrons. And of course, we call that a neutron star. If you remember from that video, we also talked about how a neutron star, because of gravity, has been crushed down to something very, very small. A typical neutron star is about the size of a major city in the United States, maybe 12 to 15 miles across. And so a neutron star has a tremendous amount of gravity crushing it down to something very, very small. And what that seems to suggest is the idea of how do we know something like this exists when it's so very small? Imagine something only 15 miles across at a distance of 1,000 light years away. How do we find these objects? How do we know that they actually exist? And so the idea of a neutron star, although it's related to the physics of what a star experiences when it undergoes core collapse, theoretically, they were first suggested in the 1930s. The physicists of the 1930s worked out the details of the physics involved in this process, or at least some of the physics involved in this process, and they realized that you could theoretically have an object called a neutron star. But the problem is they also concluded that something very, very small, such as a neutron star, would be nearly impossible to find. So the idea was basically shelved. They wrote papers about it, and then the idea was essentially all but forgotten. In 1967, that would change dramatically. There was a young woman working on her PhD in astrophysics. She was working in England. Her name was Jocelyn Bell. And she was working with her advisor on a project that involved radio astronomy. And what they were doing in particular is they were taking a radio telescope, shown in this picture here. And I know it looks very crude, it almost looks like something to hang your laundry on. But a radio telescope of this type is very, very easy to build and very primitive. It's a bunch of wires that's stretched across a bunch of support structures. And what it does is it allows the natural rotation of the Earth to essentially scan the entire sky as if it's a radio telescope pointed up at all times. And so they were studying the Milky Way galaxy, and they were studying and mapping some of the radio sources, the places in our galaxy where radio noise is produced by just natural things occurring in our galaxy. Well, when they were looking at the data every day, Jocelyn Bell noticed something quite odd, that at a particular time each day, they would get a signal that would seem to turn on and off and on and off over and over and over again. Here's a graph. And so what they noticed is this thing was turning on with brightness and then becoming dark and then bright and then dark and then bright and then dark. And here's an actual optical set of images of this very object. And so what you'll notice, I'm going to let it load one more time just so we can get that to play again. What you'll notice is how this thing is turning on and turning off and turning on and turning off and turning on and turning off. And it's doing it with this incredible regularity to it. This is the energy in radio light, I should say. This is visible light. And what they noticed is it was a pulse of bright and then dark and then bright and then dark with a period of 1.34 seconds. So something seemed as if it was turning on and turning off with incredible regularity. And they even tested how regular this pulsation was. And they noticed that the regularity of it, in other words, the timing of it turning on and turning off, was so regular, so precise, that it was actually more precise than modern day watches. In other words, a modern day timekeeping device isn't as precise as this object was. So this regular on and off seemed to be kind of odd. It was almost as if it was not natural, that something in nature couldn't possibly do this with such incredible precision and regularity. So they half-heartedly, part serious and part joking around, gave this newly discovered object a label. They called it LGM number 1. And LGM stands for Little Green Men number 1, because at first they thought maybe they had discovered evidence of alien life in our universe that was somehow signaling other forms of life in the universe. So LGM number 1 was this mysterious pulsation of light that was occurring on a regular basis. Some object in our universe was doing this. Well, they saved themselves the embarrassment of having to publish a paper that is claiming that extraterrestrials actually exist when the physicist of the day came and told them that what they had found was a neutron star. Now here's the idea. A neutron star is very, very small. Gravity has crushed it down to an incredibly small size. But the magnetic field of a core of any sort of a star is usually quite intense. The sun has a very, very powerful magnetic field. When you shrink some object that has a magnetic field down to a very small size, what happens is it intensifies the magnetic field. So they theorized that a neutron star should have a very, very powerful magnetic field. And so anything that was near the neutron star, energy that is near the neutron star, should be forced to move along the magnetic field lines. Essentially, these are high energy particles, like electrons that are charged particles moving very quickly. Because they're charged particles, they're going to have to obey the magnetic field lines. And when an electron moves along the magnetic field lines, the energy that the electron gives off is going to be concentrated on 2 spots, the magnetic north and magnetic south pole of this neutron star. Now, what they theorized is all you need is a neutron star to spin very, very rapidly in a way that where the spin axis is not aligned with the magnetic field north and south pole. So if you imagine this thing spinning around and around and around like this, what'll happen is this magnetic north and south pole will sweep around and around and around as well. Now, more about that in just a minute. Now the thing is though, is the discovery of this object, these rotating neutron stars are spinning very quickly. And the question is, why are they spinning so fast? And the idea is that if you take an object that is rotating, and if you remember from a previous lecture, we talked about how when an object that is rotating shrinks in size, it has to spin faster as a result of the fact that it's shrinking. So something that is spinning and shrinking will spin faster while it shrinks. And we call this the conservation of angular momentum. A figure skater does this whenever she pulls her arms inward while she's spinning. Of course, she spins faster and faster as a result. So this is a core that has shrunk while it was already spinning. And as it spins and shrinks, it spins faster and faster and faster. So the physics seem to be plausible that a neutron star could be spinning very, very quickly. And so the idea is that if this rapidly rotating neutron star is spinning in such a way that the energy at the north and south pole of this thing is in the direction of the Earth, every time this spins around one time, you're going to get a flash of light that flashes towards us, and flashes towards us. Let me animate that for you. So you can imagine if we slow it way down here, every time one of those poles, if it happens to be pointing in our direction, sweeps by us, you'll get that energy sweeping at us like a lighthouse would, with its beam flashing at you and then not, and then flashing at you and then not. So this rapidly rotating neutron star is an idea that seemed, of course, very plausible. And today, these rapidly rotating neutron stars are simply called pulsars. So this pulse of light that seems to be flashing at us as this neutron star is rotating is the physics of why we see these things and what Jocelyn Bell had discovered accidentally in 1967. So a pulsar is a rapidly rotating neutron star that happens to have one of its beams in the direction of the Earth And every time it spins around, that beam of energy in our direction looks like a pulse of light turning on and turning off. So in 1967, these objects were discovered. The physics of this seemed explained and seemed plausible. And then, of course, the next endeavor was, are there more? Are there other examples of pulsars in our galaxy? And let me show you one of the more famous discoveries that had happened in that time. We talked in the last video about how one of the more famous supernovas that have occurred in history in the year 1054 was the one that the Chinese astronomers had observed in July of 1054. And if you recall, centuries later, it was discovered that this expanding cloud, which is a supernova remnant, is the product of that supernova from 1,000 years ago. And if you recall, we call it the Crab Nebula. Well, astronomers had started to investigate other places in the sky looking for pulsars. And what they discovered is when they aimed their radio telescope at the center of the Crab Nebula, they actually found something flashing light on and off and on and off, on and off, over and over again, very, very rapidly. And here is another image. This is of a different wavelength, but it's the Crab Nebula. And this region right here in the box is what this box is right here. And so what I want you to notice is these are frames from a movie. And this is a very high-speed movie. So many, many, many frames a second. And what I want you to notice as we go from frame to frame, you can see the object is off, turning on, or at least appearing to turn on, and then it turns off again. So essentially it pulses, and then it goes away. It pulses light, and then it goes away. And this pulsar at the center of the Crab Nebula is pulsing light at us 33 times every single second. So many, many pulses in one single second. And today, because we have better and more sophisticated telescopes, we have the ability to study these with great detail. This is a Hubble Space Telescope image of the Crab Nebula. So this box right here is this image right here. And let's zoom in a little bit more. And what you'll notice, we're going to zoom into this box right here. And what you are actually seeing, this object right here, is the Crab pulsar. So one of the most famous pulsars in history is the one located at the center of the Crab Nebula. And you can actually see that the pulse of light, the energy coming from this thing as it turns and sweeps that energy around, is pushing the material of this cloud, causing a shock wave right here. So the Crab pulsar is one of the more famous examples of a rapidly rotating neutron star. And what's amazing, what's nice, is it is, of course, correlated to a supernova. So a star has blown itself up after the core collapsed. The supernova remnant is expanding into space. The core, due to gravity, has shrunk down to a rapidly rotating neutron star. So one final question related to this is, if gravity crushes all of this material down to make it very, very small, turning all the protons and electrons into neutrons, what has stopped the neutron star from collapsing any further? Gravity is powerful. Is there a way to keep crushing the neutrons closer and closer together? Well, the answer is maybe. When gravity is squeezing this neutron material with this incredible force that gravity can have for these objects, the amount of energy, or the amount of gravitational energy and force on these neutrons is tremendous. But what the physicists discovered is that neutrons also have a limit to how tightly they can be packed together. And so even though gravity is incredibly strong, squeezing these neutrons very tightly together, there is a limit to how tightly the neutrons can get packed together. And we call that neutron degeneracy pressure. Now, if you remember from a previous video that it was the physicist by the name of Subrahmanyan Chandrasekhar who discovered what was called electron degeneracy pressure, well, it was also Chandrasekhar that figured out that neutrons can do the exact same thing, that there's a limit to how tightly neutrons can be packed together when gravity is squeezing this material. But what he also did was he calculated, is it possible for neutrons to have the ability to hold off any powerful force of gravity, or is there a limit? And what he discovered is that if the mass of the neutron star is less than 3 times the mass of the sun, then the neutrons will fight off gravity and it'll be a neutron star forever. But if the mass of the core that survives the supernova is greater than 3 solar masses, the neutron degeneracy pressure won't work and gravity will continue to crush the object smaller and smaller and smaller. Now, what that object becomes is, of course, something quite interesting, and we're running a little short of time, so we'll save that for the next video. I hope you'll join me then.